Myself, Dr. Naresh Kumar, Associate Professor, Department of Mathematics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today, I want to discuss how we can solve Cauchy Euler's homogeneous linear differential equation. We have already discussed about this type of linear differential Cauchy Euler homogeneous linear differential equation in last lecture. But now, today, I want to solve some more problem on this topic because this topic is very important topic. Cauchy Euler homogeneous linear differential equations. The general differential equation of Cauchy Euler homogeneous linear differential equation. So this is general differential equation Cauchy Euler homogeneous linear differential equation. So in this equation there is nth differential coefficient. In first term we see that nth differential coefficient and here x to the power n in multiply means x is independent variable and the power of independent variable is equal to the order in each term. We see that in each term the power of independent variable is equal to the order of derivative and in multiply in each term. This property verify in each term. Then Cauchy Euler's homogeneous linear differential equation. Next second term is x to the power n minus 1 and here is n minus 1 derivative and power of independent variable also n minus 1. Similarly, we see in each term same property is verified. At last term we see that a naught is constant here and derivative is 0. 0 is derivative. So here multiply x to the power 0 here. Means the power of independent variable is 0. Then the order of derivative is also 0. So there is only function y. And in right hand side is some function of x, that is say phi x. So what is definition of Cauchy Euler homogeneous linear differential equation? So the power of the definition, we discuss about definition of Cauchy Euler homogeneous linear differential equation. The power of independent variable is equal to the order of the derivative in each term and in multiply in LHS from first to last term. All terms this property verify. There and RHS is some function of x. So that differential equation is known as a Cauchy Euler homogeneous linear differential equation. Now we have write again same differential equation. This is Cauchy Euler homogeneous linear differential equation. This is equation 1. In this equation a0, a1, a2, an are all constant numbers and phi x is some function of x. X is independent variable here and y is dependent variable in equation 1 is known as a Cauchy Euler's homogeneous differential equation of nth order. We will change now how we can solve this equation 1. So first of all, we will change equation 1 in linear differential equation of nth order with constant coefficient. Last chapter, this differential equation convert in a differential equation which is given in last chapter. That is linear differential equation with constant coefficient. After this differential equation, homogeneous linear differential equation, change in constant coefficient, then apply the method y is equal to Cf plus Pi. Then we can solve this equation. First of all, Euler's Cauchy homogeneous linear equation convert in differential equation with constant coefficient. Then we can solve. Okay. We will discuss here method change of variable. With the help of this method, change of variable. In our differential equation, there is x independent variable. Okay. But now this independent variable x convert to any other independent variable. Suppose x convert in z. When in our given differential equation, Cauchy Euler Homogeneous linear differential equation, we change independent variable x to z. Then this differential equation convert in linear differential equation with constant coefficient. How we can change this? With the help of this method, change of variable, independent variable. So how to change Cauchy Euler Homogeneous linear differential equation? Differential equation with constant coefficient. So here we discuss about the method, then we solve one problem on this method. Okay. To change equation 1 in constant coefficient, then we change a independent variable x to another independent variable z. We will discuss here in detail. Here following given method is known as a change of independent variable. Change of given independent variable. That independent variable which is given in our differential equation, we want to change in another independent variable. So another independent variable. Let us consider how we can change. So here some assumptions we are considering. Starting. So let us consider that the following assumptions are as follows. We consider x equal to e to the power x. This is main point. What is taking? X, let x equal to e to the power z. This result we considering here. This is equation 3. Which equation 2? 2 equation. So this is equation 3. Here x is converting z. We want to change variable x to z. So that process known as that process in which we change the independent variable x to z, that process is known as a change of variable. This is a very famous method, change of variable. Then taking log on both sides in equation 3. Log here x equal to e to the power z. Taking log x equal to log e to the power z. This z goes to before log, z log e and log x. Log is z, log e is 1. So here log x equal to z. Okay, log x equal to z. So here let x equal to e to the power z. Taking log on both sides. So log x equal to log e to the power z. Here apply formula log x to the power n. Log x to the power n formula is n log x. N goes before log. Power goes before log. So n goes before log. N log x. So here log x equal to n log e. Because e to the power z here. So z log e. What here apply again? Formula next. Log e is 1. The value of log e always is 1. So putting here log e 1, then log x equal to z. We get log x equal to z. Or we can say z equal to log x. This is equation 4. Now differentiating with respect to x to equation 4. Okay. 4 is z equal to log x. Differentiating with respect to x to z. So dz over dx equal to 1 upon x. Differentiation of log x is 1 upon x. Differential of log x is 1 upon x. So here is z equal to, here given z equal to log x. So differentiating with respect to x, dz over dx is equal to d over dx of log x, and this equal to 1 upon x, d over dx. So here we get dz over dx is 1 upon x. This is very important value, where capital D is known as a d over dx, differentiating with respect to x, that is represented d. Here capital D represented d over dx, and capital D dash represented d over dz. Z is another independent variable. This equation 5. Now then we get y1. What is 1? dy dx. 1 is dy dx. So dy dx, here dy dz into 1 upon x. Okay. So dy dx equal to dy dz into 1 upon x. So we write here from 1. Equation 1 is dy dx. Breaking dy dx. How we can break this? Multiply dz and divide by dz and interchange the variable. So here dy dz upon dx. This equation 7. Putting this value dz over dx is equal to 1 upon x in equation 7. So here then we get 1. Again we get 1 here. dy dx is equal to dy dz into 1 upon x. Into 1 upon x. This equation number 9. So now then we get y1 dy dx is equal to dy dz into 1 upon x. This equation 10. This x writing to this side. Multiply here x on both sides. Then here x dy dx equal to dy dz. So here we proof x. This is the independent variable x, and multiply with dy dz dx. This is first derivative. Here this first derivative power is 1. So power of independent variable is equal to the order of derivative. Both are in multiply. So this result convert in here dy over dz. Okay. So this result is x dy, and this result is d dash y. We have proved this result here. So x dy dx equal to dy dz. X dy dx is dy. X dy. Here is x dy. This equal to d dash y. This equation 11. Equation 11 is important equation. In our question, we apply only equation 11. This equation is important. And x to the power z, equation 3. Equation 3 is also important. Equation 3, next equation 11, we use in our question. Now, number 2, we find out value of x square d2y over dx2. So here in second term, what is in second term? The power of independent variable is 2 multiply with second order derivative. So we remove this term. So how we can find value of this? So here we discuss this second. We can write that d2y dx2. d2y dx2 differentiation of y with respect to x 2 times. So we write this d over dx of dy over dx. d2y dx2 means differentiation with respect to x of dy upon dx. dy upon dx is first derivative, and again differentiating with respect to x means dy dx of dy dx. Then we get d2y over dx2. So here we break this part into two types. d2y over dx2 is equal to d over dx dy over dx. This equation 12. Now from equation 10 is this equation. From equation 10, putting value of dy dx in equation 12. From equation 10 is this equation. Putting the value of dy dx in equation 12. Then we get here d2 by dx2 equal to dy dx of, here this is the value of dy dx. In equation 10 is given dy dx is equal to 1 upon x dy dz. We have proved this also. So here putting now differentiating this result one time. Differentiating 13 equation with respect to x using product formula. What is product formula? Differentiation of u into v. Differentiation of u into v is equal to d is equal to u is constant, differential of v plus v is constant, differential of u. So we apply this formula. This formula is known as a product formula. So here is two function dy dz and into 1 upon x. So first differentiation dy dz is constant. Dy dz is constant, keeping constant. Differentiation of 1 upon x. So dy dx of 1 upon x, this minus 1 upon x square. So we write here formula minus 1 upon x square. Dy dz is constant plus dy dx of dy dz. 1 upon x is constant here. So d2 by dx2, this equal to minus 1 upon x square into dy dz plus. How we can differentiate this function? Here inside the bracket, here is dy dz. Y is the function of z. But in outside is differential with respect to x. So we change here variable. Here should be d over dz. So I am writing here d over dz, dy over dz and dz over dx and 1 upon x. So again putting value of dz over dx is 1 upon x in equation this. Then we write here d2y over dx2 equal to minus 1 upon x square dy over dz plus d over dz, dy over dz, dz over dx into 1 upon x. But dz over dx is 1 upon x here. So this value putting here. Then we get here minus 1 upon x square dy dz plus d over dz and dy over dz. Putting this value here. Dz over dx equal to 1 upon x. So 1 upon x into 1 upon x. Again d2y over dx2 equal to minus 1 upon x square dy over dz plus this differentiate d over dz of dy over dz. This is equal to d2y over dz2. Same variable here. So here 2 times differentiating of y with respect to z. Then we get d2y over dz2. So here d2y dz2 and 1 upon x into 1 upon x. This is 1 upon x square. So this is equation 16. Equation 16 is most important equation. You want to understand how we can find this equation 16. So now 1 upon x square is common. We write positive first term and negative last term. So this d2y over dx2 is positive. We write this. This is negative term. We write this. And 1 upon x square taking common. So this x square, this multiply here x square on both sides. Then we get x square d2 by dx2 equal to this d2y over dz2. This equal to d dash square y. dy over dz equal to d dash y. This both value putting in last formula this. d2y dz2 is d dash square y. dy over dz is d dash y. After putting this value, we get this result. Now d dash is common here. D dash is common here. Then we get d dash minus 1. And y is common in right hand side. Y is taking common in right hand side, not left hand side. Because y differentiate here. If you are taking y to left side common, then question is wrong. 100%. Here y is derivative with respect to z here. So y is function, y taking right hand side. Similarly, we can prove other result. X cube d cube by over dx cube equal to same result. Here we get d dash minus 1. Here x square d2 by dx2. If in our question we see that here is x square d2 by dx2. Okay, then we get here result d dash minus 1 into y. This is equation 17. Similarly, in our question x cube d cube by over dx cube. If the power of independent variable is 3 and order of derivative is 3 in each in term and multiply both, then we find here d dash minus 1 d dash minus 2 into y. This is very famous formula. We write here directly this, but with the help of this last two equations we can prove this. Okay, so next is x cube d cube by. Here x cube d3y over dx3. This is x cube d cube by. So value of this result is d dash minus 1 d dash minus 2 into y. This equation 19. I am using this formula in our question 19 formula. So now finally we see that first formula is x dy dx equal to dy dz. We prove equation 11. How we can prove? We discuss in detail in last slide. So you study of last slide is thoroughly. Then you can understand this formula. We proved here x dy dx equal to dy dz. Here is variable x, here variable is z. So x convert in z. Finally, x dy equal to d dash y. This equation 11. Very important equation 11. We apply in our question the same formula 11. And formula is 2 x square d2y dx2 equal to d dash minus 1 y. Means x square d square y equal to d dash minus 1 y. This equation 17. 17 also very important. Next formula x cube d cube by equal to d dash minus 1 d dash minus 2 by. Okay, this equation 19. And one result is x equal to e to the power z. This equation 3. 3 equation, 11 equation, 17 equation and 19 equation. Equation 3, equation 11, equation 17 and equation 19. With the help of equation 4, equation 11, equation 17 and equation 19. With the help of these four equations, these four formulae, we can change the given Cauchy Euler homogeneous differential equation in linear differential equation with constant coefficient in independent variable x to z. In our question, variable is given x and we want to change the variable x to z. Then converted question is known as a linear differential equation with constant coefficient. So here I want to solve one problem based on this topic. So here problem 2. One problem we have solved in our last lecture. But this is problem 2. Problem 2 based on Cauchy Euler homogeneous linear differential equation. So you should understand this problem thoroughly. I want to discuss the solution of this problem is thoroughly. So solve, what is question? Solve here x square d2y over dx2. Here is x square. Here is d2y dx2. Here is independent variable. The power of independent variable is 2. Here is order. Order of derivative is 2. Both are in multiply. So we check out the power of independent variable equal to order of the derivative and both are multiply and this property lie in each term, then that equation is known as a Cauchy Euler Homogeneous Linear Differential Equation. And we want to change this equation in linear differential equation with constant coefficient to one variable to other variable. In our question is x variable here, y and x. This is x independent variable. But we change this problem in x to z. Z is another independent variable. After converting x to z, we get the equation constant coefficient. In second term is x dy dx plus y. Same property, first term and second term. Same property lie in last term also. Here is x to the power 1 and multiply with first derivative. So this property verify. Here is y, no derivative, but x to the power 0 here. This is right hand side is some function of x here. Sin log x square. This is problem given in our question. So how we can solve this question and discuss the solution. Solution, we write the same question. This equation 1 here. D over dx is capital D. D over dx I am writing capital D. Okay. So this dy dx is dy. Dy dx is dy. D2y dx2 is d square y. D cube y over dx cube is d cube y. This equation 2. This is d form derivative. D over dx we write d. 2 time differential. D2 over dx to be write d square. Here is y. Then here is y. Here is y. Then here is y. So dy dx is dy. D2y dx2 is d square y. So now equation 1 with the help of equation 2 can be written as the following. Here x square d2y dx2. Writing x square d2y. X dy dx. Writing x dy plus y equal to sin log x square. This equation 3. Now same discuss problem. How we can change. So let us consider same this result we are showing in our solution. Without showing this result, you cannot get good mark. That following assumptions we have discussed already. But when you start the solution, then again showing this result. So let x equal to e to the power z. Then taking log on both sides in 3 we get log x equal to log e to the power z. Here apply formula log x to the power n. That is n log x. So I am writing here log e to the power z, z log e. Apply formula log e is 1. So log e is 1, then log x equal to z or z equal to log x. Differentiating with respect to x to equation 5, then we get dz over dx equal to 1 upon x. D is d upon dx. D dash is d over dz. D over dz means differentiating with respect to dash, represented by d dash. Differential with respect to x, represented by capital D. According our above assumptions, we get the following result. Just I am saying that these results are very important. So you see here number 1. In our question is x dy dx. X dy dx is dy dz. This equation number 8. X dy dx is x dy. This equal to d dash y. This equation 9. Left hand side, term are left hand side. These are given in our question. And we convert the term right hand side to the question. So here next x square d2y over dx2. We write here d dash square y minus d dash y. What d dash x square d square y equal to d dash minus 1y. This equation 11. So here next term x cube by dx cube equal to 1 upon x cube is common. D cube by over dz cube minus 3 d2y over dz2 plus 2 dy over dz. X cube d cube y over dx cube equal to this x cube taking this side, multiply by x cube, cross multiply. So this x cube taking this side. So x cube d cube y over dx cube equal to d dash cube by d cube by over dx cube be let d dash cube by. So this result writing here d2y over dz2 dx2 equal to, here is z, this is z, so d dash square and y. So I am writing here d dash cube by minus 3 d dash square y plus 2 dy. So y is common in right hand side. So d dash cube minus 3 dash square plus 2 d dash. So d dash is common in all terms. Here is d dash square. D dash is common here. So here is d dash square minus 3 d dash plus 2 and into y. Factorizing this result. After factorizing, we get this. So this is equation 13. Putting value from equation 4. What is 4? 4 equation is x equal to e to the power z. This is equation 4. 4 equation. So from equation 4, equation 9 and equation 11. Putting in equation 3, then we get equation 14. So our question convert in this equation 14 after putting these values. So here first value is, this is the d square y over dx square. X square d square y over dx square. So d dash minus 1y plus d dash y plus y equal to sine log x square. In our question is x square. So x square, x equal to e to the power z. So x square equal to here e to the power z ka whole square. E to the power z ka whole square. So now multiply by d dash here. D dash square minus d dash y plus d dash y plus y equal to sine log this 2z multiply 2z. Again d dash square minus d dash plus 1. This y is common. Y is common here. So sine log e to the power 2z. So this dd cancel. D dash square and plus 1 into y equal to sine. This 2z goes to left. Formula is log x की power n. Formula is log x and log x. So this 2z goes this. Sine 2z into log e. What log e is? 1 here. Log e is 1. So here sine 2 dash. D dash cancel. Finally, we get d dash square plus 1y equal to sine 2z. This is 16. That question which is given in our question paper. In our question there is x independent variable. But now applying these formulae, equation 4, equation 9, equation 11, and after putting these values in equation 3 given question, then we get equation number 16. And equation 16 is known as a linear differential equation with constant coefficient in variable z. Question is given in variable x, but after converting this, we get question in z. So now, d dash square plus 1y equal to sine 2z. This is equation 16. So this is the type of equation. This is type of equation. What is type of equation? F d dash y equal to q. F d dash is this function of d dash. Q is sine 2z. Where f d dash is d dash square plus 1 and q is sine 2z. The solution of equation 16 is in two parts. This is equation 16 is known as a linear differential equation with constant coefficient. So we get the equation solution of 16 equation in two part. This is constant coefficient. Every equation which is constant coefficient, then we find solution in two part. If Q is given in our question, so first solution is known as a CF, complementary function, and second solution is known as a PI. We have discussed this topic detail in last lectures. So first we find CF of 16 equation, complete solution of 16 equation, complementary function and particular integral. There are two solutions. So one by one we find, first find we complementary function, after we find particular integral. First we find complementary function of 16. If we want to find out the complementary function, then Q must be 0. Be putting Q equal to 0 here. Putting Q equal to, Q is sin 2z. Sin 2z taking 0 here. So equation 16 convert in 17. In right hand side, this sin 2z. Sin 2z taking 0. So here d dash square plus 1 into y equal to 0. This equation 17. We can find CF of 17. So putting d equal to m and removing y from equation 17, then we get an auxiliary form of 17. Okay? Auxiliary form means equation in m. So we get m square plus 1 equal to 0. This equation 18. This is an auxiliary form. Now factorizing of equation 18. How we can factorize this equation? M square plus 1 equal to 0. M square plus 1 equal to 0. So M square equal to this plus 1 taking right hand side. So right hand side 0. So M square plus 1 is 0. So M square equal to 0. This one goes minus 1. So M square equal to minus 1. M square equal to minus 1, where I square is minus 1. Means minus 1 is I square. So here M square equal to I square, and factorizing this, M equal to plus minus I. Now the solution of an auxiliary form, we get roots of M, we get imaginary roots, we get M equal to plus minus I. So here writing 0. So 0 plus minus I. So these roots are in type of M equal to alpha plus minus I beta. So roots of an auxiliary form are imaginary, where alpha is 0, beta is 1. Formula for CF, we apply here formula for CF of 1 if roots are imaginary. This is formula for complementary function of question. So here CF equal to e to the power alpha x in bracket C1 cos beta x plus C2 sin beta x. Putting value of alpha and beta. So we get here CF alpha is 0, e to the power 0x, C1 cos beta, beta is 1, C1 cos z plus C2 sin z. Because our equation 16 is given in z. So we write complementary function in z and particular integral in also z. At last, we putting the value of z equal to log x. So CF is C1 cos z plus C2 sin z. This is equation 20. This is the complete complementary function of 16 in z. Now, second solution of equation is 16 is PI, particular integral. So formula for PI we apply here. Pi equal to 1 upon fd dash into q. Because this question is given independent variable z. If there is z variable, then derivative is d dash. So fd dash into q. This equation 21. Putting value of fd dash and q, both value, function of d dash and value of q. Putting in equation 21. Then 21 convert in 22. Pi equal to 1 upon d dash square plus 1 into sin 2z. This is q. This is f d dash. This is equation 22. We have last cases for particular integral if trigonometrical function is given there. Sin ax or cos ax. This function is given in our question. Then we putting d square equal to minus a square. This value putting. We have already discussed about this topic in detail. So we are not discussing here direct putting value. So putting here d square equal to minus a square. This equal to minus a is here 2. Sin ax, a is here 2. So minus 2 ka square. Minus 2 ka square is minus 4 in 22. Then we get solution. If f minus a square, this is the condition. This is the first condition of particular integral. If trigonometrical function is given there. So f minus a square is not 0. So I am writing here pi equal to 1 upon minus 2 square plus 1 sin 2z. This is 23 equation. Pi equal to minus 4 plus 1. My 2 ka square 4 minus 4 plus 1. So minus 1 upon 3 sin 2z. Here denominator is not 0. Here denominator is not 0. Is not 0. Is not 0. Denominator is not 0 here. If denominator is 0, then we change formula again. We apply condition second. So now denominator is not 0, then we get complete solution. So here minus 1 upon 3 sin 2z. This equation 24. This is complete PI of equation 16. So equation 24 is complete PI of equation 16 in Z. Here both solution we find in Z because first question which is given in question paper, that is given in x. After converting this in constant coefficient, then we get equation 16. Equation 16 is given in Z variable, y and z. Z is independent variable. So now then we solve equation 16 in complementary function and particular integral. So complementary function also find in Z and particular integral is also find in Z. So now complete solution of 16, we apply formula y is equal to CF plus PI, complementary function plus particular integral. When we adding both solution, then we find complete solution. So here y is equal to, this is CF, C1 equal to cos Z plus C2 sin Z. We write here variable Z and minus 1 upon 3 sin 2Z. This is 24 equation in Z. Now putting value of Z at last Z convert in X. When we converting Z in X, then we get our first question, solution of first question. So here what is Z? Z is equal to here log X, because we let here X equal to e to the power Z. This is the first assumption. So putting Z equal to log X in this solution 24. So finally we get y is equal to C1 cos, this is Z, Z is log X, C1 cos log X plus C2 sin log X minus 1 upon 3 sin 2. Here is 2Z, sin 2Z, sin 2Z, Z is log X. So sin 2 log X. So this is the complete equation 25. 25 is complete solution of given question in question paper, in which question X is independent variable. So we find solution in equation 24. In 24 is Z independent variable. After putting value of Z in 24, we get equation 25, and in 25 is X variable. So this is the solution of equation 1. So this is the complete solution of equation 1. Okay. So this process we can apply to solve Cauchy Euler Homogeneous linear differential equation. First of all, we change Cauchy Euler Homogeneous linear differential equation in linear differential equation with constant coefficient. Then we apply formula y is equal to CF plus PI. So first solution, we find y is equal to CF plus PI in independent variable z. Then last solution, after putting value of z, we get solution of given question in independent variable x. So this is the basic concept to find the solution of Cauchy Euler Homogeneous linear differential equation. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.